Moving on to the next presentation, I would now like to invite Mr. Hans Wouters, Managing Director for Brightwork Netherlands. He's going to talk about Sand Cycle, a new game-changing RFID-based instrument in sand filter applications. Over to you, Hans.
Thank you very much. Thank you very much for giving me the opportunity to speak at this India Water Innovation Week, and particularly about the topic which we have been dealt with in the last couple of years, and which has been successfully implemented in Europe. It is indeed an innovation which I think might be game-changing, and that's the reason why I'm very happy to exchange our journey in this innovation process and to show you what we've been doing. Next slide, please. The presentation I've built up in a few blocks. First of all, I would like to show you what the core component in the water treatment system looks like. It's about a sand filter, a particular type of sand filter, continuous sand filtration, and its applications. I have a case study from the UK where we are talking about biological nitrification in this particular sand filter. Then a case study in the Netherlands, which is about biological denitrification in the sand filter. And the last case study I would like to show you in a sheet is about Kaatsheuvel, phosphorus removal. And then I would like to give you an idea. Oh, not too fast. Could you go back, please? One again. Thanks. And the last bullet in this content sheet is about sand cycle remote monitoring and control. And basically that is the majority of the presentation, because that's what the innovation is all about. Next one. Yes. Next one, please. The continuous sand filters are sand filters which are used for a variety of applications in groundwater treatment, in surface water direct filtration, cooling water, wastewater for primary filtration, and wastewater for all kinds of tertiary filtration applications like solid removal, nitrogen removal, phosphorus removal. And the reason why all these applications are possible in the filter is that the filter itself is a very simple setup. It's a setup where the filtration is taking place at the same time as where the washing of the sand grains are taking place. And I would like to explain you that in a few sentences in this cross section. The feed water comes into the filter, let's say at the distributor arms, which is at the bottom of the filter, and then the water is flowing upward through the filter into the filtrate room and then leaves the filter at the top. And as you can imagine, solids will build up in the filter and needs to be discharged from the system. That is executed by an airlift principle, which is basically a pipe in the center part of the filter from the bottom to the top, in which a little bit of compressed air is blown, which sucks the sand into the airlift to the top, and there the sand is separated from the solids by a little bit of filtrate flow flowing upwards through the labyrinth at the top section of the filter. So what we get is a feed flow coming in, a continuous filtrate flow coming out without any solids, and a washwater flow which contains all the solids which has been trapped in the filter bed. And this continuous process will take place 24/7. And that's nice, because in this case you can use the sand filter not only to remove solids, but also as a carrier material for biomass, for nitrifying applications, for denitrifying applications, and a lot of other applications. And because of this simplicity of the process, it is a stable and robust process which will work and which will create a solution for a variety of applications. Next slide, please. In this sheet, there is an example of a biological nitrification process in these filters, where the nitrifiers are growing on top of the sand grains. You can see a grain size where a little bit of biomass is sticking to the sand grain in patches, in black patches, and these patches will contribute to the conversion of the ammonia into nitrate. And this proved to be a very effective process. Throughout the filter bed, we will have this biomass present, and it will then nitrify all over the filter bed height. In the graph, you can see the ammonia load and the ammonia conversion, which almost coincides, which means is that the ammonia is fully removed throughout the filtration process in the continuous sand filter. Next sheet, please. This is another example where we are not talking about nitrification, but denitrification, biological denitrification. And in this case, we are trying to remove nitrate into nitrogen gas by denitrifying biomass. These are heterotrophic bacteria which can exist under anoxic conditions. So that means is that the system needs to be run at conditions with very low oxygen concentrations. Typically, a carbon source is dosed into the feed of the filter, and then you'll get a conversion process which looks like as indicated in the graph, where the feed nitrate is in the range of 10 to 25 milligram per liter, and the filtrate pink data set is consistently on the, let's say, 3 milligrams per liter. It's a very stable process, and you can steer that, you can control that very nicely by dosing the right amount of carbon source in function of the oxygen concentration in the feed and the nitrate concentration in the feed. Conversion rates up to 5 kilograms of nitrogen per cubic meter of bed volume per day can be achieved. It's a very elegant process. Next sheet, please. Another application is related to phosphorus removal. Phosphorus removal is a process which is not biological, but a physical chemical process. In this case, the continuous sand filter is used to remove the phosphorus components, the soluble phosphorus components, by dosing ferric or alum into the feed pipeline to the filter. And then by doing so, the soluble phosphorus is becoming insoluble in iron phosphate flocks, which are then removed very efficiently in the filtration process. Typical feed levels are in the range of 1 to 5 milligram per liter of total phosphorus, while filtrate levels can be as low as 0.1 milligram per liter of total phosphorus. In the data set in the graph at the bottom part of the sheet, you can see the average influent total phosphorus and soluble phosphorus, and the average effluent total phosphorus and soluble phosphorus concentrations. And this is throughout a number of years a very stable phosphorus removal process. In this case, the wash water is typically rinsed and fed back to the head of the works of the wastewater treatment works, and there it will be trapped into the sludge, in the activated sludge, and finally discharged from the system through the waste activated sludge. So this is a very simple setup which proved to be very effective as a tertiary solution to remove phosphorus to very low levels. Next sheet, please. Then I would like to focus a little bit on the application where we have been dealing with in the last couple of years, and that is that we would like to understand better how these filter systems could be operated in the most optimal way. And because the system is very simple, doesn't mean that you cannot optimize it to a certain extent, and that's the reason why we would like to know how the system is running under varying conditions. We also saw is that with the existing number of references, a lot of operators tend to not attend the system very well, which means that anomalies might occur. That means that after a while you'll find out that part of the sand has been lost, or some of the sand is blocked into the filter, and then the filter is operating not optimally anymore. And what we would like to do and what we would like to develop is to create a system which detects that in a very early stage, and which also helps the system to be operated in the most optimal way. Now, how that looks like, that's what you can see on the next sheet. That is what we call the Send Cycle Remote Monitoring and Control System. Basically, the system is based upon the use of RFID tags. These RFID tags are commonly used in Europe by to identify, for instance, a cat or a dog. And then, if your cat or dog is lost, you can detect it by the unique number of the tag, which is implanted in the cat or the dog. Also, if you have a cat lock, then your cat can come in. The neighbor's cat cannot, because the unique number of the neighbor's cat is not identified by the lock of the cat lock. This principle of these small RFID tags have been used to apply those in the water sector, and more particular in our continuous sand filters. So basically what we do, we are using these small tags, which are a little bit bigger than a sand grain, throw them in the sand filter, and then they will circulate around with the sand. And by detecting these individual tags every now and then, we know how fast the sand is moving and whether the sand is moving continuously and homogeneously. That is generating a lot of data, which helps us to optimize the overall system. Next sheet, please. This is a very simple diagram of what the flow of data looks like. The sand filters at the top left corner are generating field data. The tags are identified by antennees in the filter, and these unique numbers and time stamps of each data set is then sent through a decoder into a data logger and is flowing into our web server. In the web server, we are converting those field data into dashboards, and these dashboards are then sent back to the operator, which can have access to that 24/7. And I will show you a dashboard in a minute, but with that, the operator can quickly look at what is going on and how it is functioning. Could you go back to the last sheet, please?
Hans, we have 2 more minutes.
Yep, that's fine. Here you can see the antennae and also the tag on the photograph. Next sheet, please. This is a dashboard showing a green area where the system is running properly, and the red area where the system is starting to deviate, and then automatically the operator is giving the feedback in order to take some proper actions. I'll not go into the details of the other pictograms in the dashboard, but if you like, I can explain to you in a separate dialogue. Next sheet, please. This is what I would like to pinpoint further, is when we are monitoring the system's behavior, we can also optimize the behavior. And by doing so, we can start to improve the performance, both for biological applications as for solids removal applications. This is a typical graph on the left-hand side of a non-controlled system and on the right-hand side of a controlled system. Well, basically, we are trying to interfere with the sand circulation movement and getting the sand circulation movement in a region where the most optimal filtration results are there. And by continuously monitoring these tags, we are able to do that. And we can then actually try to optimize the performance and get the most out of the filtration system. Next sheet, please. This is what we applied at various sites. This is an example of a site in the UK where we used the tool as an autopsy tool to find out how the system is running and whether it was not running properly, how we could remedy that. and it is very powerful to use this then as a tool to take the proper actions. The next sheet is the last sheet. What is my takeaway message? I think one of the first things is that the continuous sand filtration is a very powerful and multi-purpose treatment technology in both water and wastewater. Sand cycle proved to be a very successful remote monitoring and control tool for these filters. And I think that it also has added value to other water and wastewater treatment components. That's what we are working on at the moment. And I think that will pave the way towards further applications which are creating added value in the overall optimization of water and wastewater treatment schemes. Thank you very much for your attention. Any questions?
Thank you, Hans. We have one or two questions for you. I think first question is that does the sand media have to go through any preparation or treatment before it is being used?
No, we typically apply sieved river sand. So the sand needs, of course, to be prepared before you can use it as filter sand, which means is that it is sieved in a certain fraction. And then it can be used, and it will be used in these filters for quite a long time. So it doesn't need to be replaced because of wear and tear, because there is no wear and tear if the proper material is selected.
Hans, one more question is, what is the sand quality? Is it the same as used in RGF?
More or less, yes. What we typically use is river sand instead of mine sand. In RGFs, also mine sand is used, but we would like to have more rounded sand in order to get the sand circulation properly taking place. But you can compare those two media for RGFs and continuous sand filters very well.
One final question I will take, Hans, is that is one sand filter enough for the entire purification? And when are these filters clean?
You mean for the entire purification of municipal wastewater, or what do you mean?
I think that is what the question is.
Sorry?
I think that is what the question is referring to, municipal.
Yeah, well, in most cases, you need to have a biological treatment first to remove most of the organic matter in an activated sludge plant or an MBBR or whatever, and then the system can be used very effectively as a polishing step to create very low levels of nitrate, of nitrogen and phosphorus, and also it can be then very effective to reuse the water for all kinds of purposes. So see it as a final stage of a municipal wastewater treatment works as a stepping stone towards water reuse.
Thank you, Hans, for your wonderful presentation. We have been receiving good feedback for it in the Q&A box. So thank you very much, Hans.
Thank you.
Moving to our next presenter, Dr. Clive Lipchin. He is a water management expert with Saaf Consult, and he is going to talk about evidence-based wastewater monitoring and policy for addressing the COVID-19 pandemic, specifically his experience in the Israel and the Palestinian territories. Dr. Clive?
Thank you very much. Thank you so much for this opportunity to present this work in this very esteemed conference, and to all the colleagues that are online at the moment. So first, next slide, please. Sorry. So just a brief about Saaf Consult. Saaf Consult is a environmental consulting company based in the Netherlands. And we are active in many parts of the developing world. We do a lot of work in the MENA region, Middle East, North Africa, South Asia, and West Africa. We focus specifically on water and related energy issues. So the water energy nexus is a focus of our work. We bring to the fore contemporary solutions, specifically trying to integrate into our work technology, IT, and we hope a dose of common sense to our work. We have a broad and wide contiguous international network, and currently we are implementing projects to help with the response to the COVID-19 pandemic. Next slide, please. So what we're talking about here is what is being termed in projects and in the literature dealing with this issue, what is called wastewater epidemiology. And simply this means that as we develop tools to identify various what we call contaminants of emergent concern, or CECs, pathogens, viruses, problematic hormones, and so on, all of these are going to be found in the wastewater when we excrete these pathogens into the sewage. So there is a growing appreciation of using wastewater as a means for assisting and developing public health policy and projects. This, of course, is very relevant to the current challenge of the COVID-19 virus. The entire world, of course, is being impacted by this. And the issue is really a tension between putting into place the appropriate public health measures to control the spread of the disease, but doing that with trying to minimize as much as possible, of course, the economic impact of lockdowns, which all countries have in some form or fashion instituted and are currently instituted. So what we are saying here with wastewater epidemiology is that there's an opportunity to identify a sustainable tracking model that will allow us to reopen the economy while continuously monitoring for outbreaks of the virus. This is because by using wastewater epidemiology, we can identify outbreaks of the virus by regularly sampling across sewage networks. And in this way, we can develop an early warning system of where a outbreak is expected to occur before that outbreak actually happens. So we need to take our wastewater sampling through the wastewater epidemiology approach, map this on the sewer networks using, of course, tools like GIS and other mapping services, compare and correlate that with public health data on testing of individuals that are symptomatic for the disease. And together we can provide a more comprehensive package to health officials so that they can be more prepared and aware of dealing with the virus in terms of future outbreaks. Next slide, please. So just some statistics for India, given that this is a conference being sponsored by colleagues from India. So these are statistics that I found on the internet just this week. So the number of confirmed cases in India at the moment is over 6 million, with about 3,000 new cases per day. As you can see, of course, and good results, most people are recovering from the disease, but there's still something at least of about 100,000 deaths. Now, these statistics are misleading because these statistics are based on individual testing. In other words, these statistics are based on the ability of health authorities to test and identify those that are positive for the disease based on individual tests. But this does not in any way relate to the number of potential carriers of the disease, because as I think most people are aware, most people that are carriers for the disease are asymptomatic. And of course, if you are carrying the virus and you're asymptomatic, you are not going to get tested. So in many cases, the numbers that we see here, and of course, these are numbers that are being presented for all the countries around the world, are probably not accurate. And so we don't really get a full picture of the spread of the disease because we are not being able to showcase or identify or quantify the asymptomatic, those that are carrying the virus and are spreading the virus, but they themselves not showing symptoms and therefore not being brought into the overall statistics of the disease. So we are definitely undercounting the number of infected, and we don't really know to what level, to what percentage we're actually missing those that are actually carrying the virus but not showing symptoms themselves. Next slide, please. So wastewater epidemiology can help us to track the disease, specifically in those that are carriers and are asymptomatic, and give us an early warning system before an outbreak actually occurs. So this is an example of a study that was carried out in the United States by researchers from Yale University. And you see two things in the slide. Firstly, you see quite a strong correlation between actual cases of the virus, that's the black line, and what we see in the sewage. But what you see, very interestingly, is that we are able to determine from our wastewater epidemiological approach 1 week prior to the actual outbreaks. So this is a very good example of how we can do a pre-screening of the disease and prepare for future outbreaks before they happen. Next slide, please. Next slide. Okay, so to summarize the approach, we use the term stream tracing because, of course, we are looking at identifying the virus along a sewer network. And I'm going to use as a case study a project that we're now launching in Israel and in the Palestinian territories. Now, in Israel, we already began to be looking at this issue back in 2013 when there was a polio outbreak in Israel's southern region. And we identified the virus, the polio virus, in the sewage. And we were able to very quickly lock down the communities that were at risk of infection. And very rapidly were able to prevent the spread of the virus. And thankfully with polio, of course, we have a vaccine. So as soon as we knew which communities were at risk, we put into place a vaccination program. And the polio virus did not spread beyond the communities. And within a couple of months, we were showing no instances of any polio virus in the community. So already back then, there was the appreciation of using wastewater as a screening tool for viruses. And of course, now we're bringing this to the COVID reality that we're all facing. So currently, raw sewage data is being collected for our COVID-19 study. This data is representing specific districts, as I'll show you in a second. We then cross-link this data with the number of infected people from each location. We get that information from the Ministry of Health. And this allows us to derive and provide quantitative surveillance tools, specifically to estimate the extent of outbreaks and their spatial distribution based on our sewer measurements. And secondly, to provide early warning systems to the authorities so that they can quantitatively and efficiently put into place effective lockdown measures or reduction of people's movement and so on to minimize the spread of infection. Secondly, in addition, a virus concentration method has been developed for the COVID-19 strain in sewage and relating this to local populations and their geographic information. So we have within our study and in studies that have been carried out in many countries around the world, a proof of concept that sewage associated virus data is a reliable epidemiological tool. It is also a much more economic and efficient tool than individually testing people. In other words, there's a strong economic incentive to bring in wastewater epidemiology because it's much cheaper than going out and having to test individually those that are symptomatic for the disease. Next slide, please. So another element of our work, which is an area of departure from most of the studies that have been done in other parts of the country, is the reality that most of the world actually is not connected to a sewer grid, what we can call off-the-grid communities. So some statistics in the slide, something like 1.3 billion people have limited access to water, sanitation, and electricity. And many of these people live in rural and semi-rural communities. And until we are able to provide sufficient water, energy, and sanitation services to these communities, little progress, of course, can be made to develop their economies and to improve their lives. In addition, because of their lack of access to these water and wastewater infrastructures, these communities are at some of the highest risk for infection of the COVID-19 disease because of their lack of ability to provide appropriate sanitation and hygiene. As well, of course, these are communities that are many times crowded with very minimal living conditions. So things like social distancing for these communities are also very challenging. So in our study, we are taking wastewater epidemiology to another level. We are not only using this approach to check or identify for the virus in communities linked or serviced by sewer networks, but also broadening the study to provide this methodology to communities that are not serviced by sewer networks, which is huge numbers of people all across the world. Next slide, please. So in our specific case study, the off-the-grid communities are something like this. Around 70% of the Palestinian population in the West Bank is not serviced by sewer and wastewater infrastructure. In Jordan, our neighbor to the east, it's approximately 30%. And in Israel itself, we are looking at around 50% of the Bedouin population, which is an indigenous community in the south of Israel, in the Negev Desert. Around 50% of the Bedouin population is also off the grid. So these are our most vulnerable communities to infection. Next slide, please. We are working with two companies, two private sector companies that have developed technologies and methodologies to survey for the virus in sewage. Firstly, we're working with an Israeli company called CanDo, which has developed automatic samplers, as you can see in this picture, which you could put into the sewers and can generate samples over a 24-hour period. And then you can take those samples to the lab. This gives you a more comprehensive picture of the spread of the virus, as opposed to simply going into the field and taking grab samples, which only gives you a sense of what the concentration of the virus is at a single point in time. So we work with CanDo in giving us more comprehensive assessments of the concentration of the virus in sewage. Next slide, please. Okay. We're also working with KWR in the Netherlands. So already we've had some talks prior to mine from colleagues from KWR. KWR is a pioneer in wastewater epidemiology, working on COVID, and we're working with them in our study, specifically in terms of communication of data analytics, and developing communication strategies for local and national authorities. Next slide, please. So specifically in this map is our case study where we are working. What you can see here, hopefully you can see my mouse. So this green line is the border between Israel and the West Bank. These areas in purple are Palestinian communities in the West Bank. Hebron is the largest city in the region. We're looking at a roughly 500,000 population, but everything that you see in purple are communities that are off the grid. In other words, there is no sewer network in these communities. And so what is happening is that the sewage is either being discharged directly into the environment in open sewage channels, or being indirectly discharged into the environment via porous cesspits. As we go from the Palestinian territories into Israel, we see here the Israeli side. The areas in green are communities that are connected to sewer grids, so they have the infrastructure and sewage is well managed. The yellow areas are Bedouin towns that have service to networks, and the orange are Bedouin communities that are not connected to networks. So within the study area, we have a mix of what we can call on-sewer communities and off-sewer communities, as well as open sewage channels, which I'll show you, I think, the next slide. Next slide, please. So this is an example of what happens when there is no access to sewage infrastructure. Sewage is simply discharged freely into the environment, and this is a major public health risk, as well, of course, as an environmental risk. So this is an example of sewage being discharged in the West Bank, and what's interesting about this picture is you can see here the linkage between untreated sewage and people's health. So these are goats and sheep that are being herded in this region by local Bedouin, and these animals are going to be eaten by the community. So any contaminants of emergent concern, pharmaceuticals, viruses, pathogens that are in the wastewater will be collected and concentrated in the fatty tissues of these animals, which will then be eaten. So there's an epidemiological pathway between exposure to sewage and people's health. Just another point that another example of this problem is that sewage that is channeled through this river system is also infiltrating into our groundwater and is posing a long-term risk to drinking water quality as well. Next slide, please.
Clive, 2 more minutes.
Okay, I'm wrapping up, thank you. This is a map showing you where we are sampling. The yellow dots are where we have done our first preliminary sampling. Next slide, please. This is just a picture of some of my colleagues where we are taking samples from the sewer. So of course we have to have the appropriate protective gear. We collect our samples and then they go to the laboratory for analysis. Next slide, please. This is just a closer look at our sampling sites. And what I just want to point out is this area highlighted, sorry, go back, thank you. Highlighted here in yellow is where we are sampling in the sewage channel itself. So if you remember the previous picture, we are sampling at 2 sites in the river, which is off-grid. And then these other sampling points here and here are where we're sampling on-grid. Next slide. Okay, this is my final slide. This is a summary, a very preliminary study of some of our results. We are only at the beginning of our work, but sorry, just go back to that slide. Okay, if you can just stop there, thank you. This is my final slide. So I just want to point out 2 things here. If you look at the last 2 columns, these are concentrations of the virus that we found in sewage. And these indicate presence of COVID in these communities, but these communities are on the grid. These are sewer communities. The first 2 sample points here, what's called Umbatin 1, Umbatin 2, is where we sampled in this open sewage channel in the non-sewer. As you can see, we found no indication of the virus. That doesn't mean the virus is not in the sewage. It means that we have to still think through how to develop the appropriate sampling methodology. The biggest challenge we are finding is when the virus is discharged into the environment, it is diluted by an order of magnitude that we do not find in sewer grids. So one of the challenges is the dilution factor. And our future sampling, which we hope to launch in the next couple of weeks, will include rethinking how to overcome the dilution factor so that we can show evidence for the virus in the non-sewer community. Once we have developed that methodology, we believe that our work can be very, very, very relevant to communities across the world, including India, of course, and other countries in Africa and the Asian subcontinent, Latin America as well. And we at Saaf Consult are very interested to explore opportunities with relevant partners where we can roll out some of this work and assist the authorities, but of course assist the communities to better manage the COVID epidemic. Thank you very much.
Thank you, Clive. We have a question from the audience. It says, by what means can we disinfect COVID virus in sewage once it is detected?
Okay, so it's important to understand that detecting the virus in sewage, it doesn't mean that there is a risk of infection. When the virus enters the sewage, when you excrete the virus from your body into the sewage, the virus is no longer active. It's not infectious. It actually breaks down into its RNA fragments. So there isn't a concern of getting infected directly from sewage. It's more the fact that you are being able to identify the virus as an indicator of infection, but there is no risk to infection directly from the virus in sewage, as far as we currently know and far as the science is currently telling us.
So one more query, Clive, is that what's the virus identification method and the time taken for the result?
So the identification method is once we extract the samples from the sewage, we use qPCR analysis to identify the virus. There are some very unique and proprietary testing methods to identify the virus in wastewater. The results are very, very rapid. If you have access to qPCR, you can get the results literally within a couple of hours.
Clive, we have two or more questions for you, but I'll take that post, our presentations are over because we have our other presenters waiting. Or, you could go into the chat box and answer those specific questions that are, addressed to you. Moving on to our next presentation, I would now like to invite Max Radermacher from Obscape. He's going to talk about affordable real-time catchment monitoring. It's a case study of Durban in South Africa.
Thank you
Max?
so much for the introduction, Kailash. All right. Good day to all of you. My name is Max Radermacher. I work at Obscape as a director. We are based in the Netherlands and in South Africa. Next slide, please. I am going to present a case study from Durban, South Africa, where we have implemented an affordable real-time catchment monitoring system. Next slide. Our partner for this project is the Durban municipality, or the eThekwini municipality as they are officially known. And in the map you can see the area that's being covered by the municipality. It's a large municipality with 100 kilometers of coastline, and the large city of Durban is situated inside its borders. 3.7 million inhabitants. Next, please. It's a very complex environment as well. You can click one more time. And there are 4,000 kilometers of rivers and streams inside the municipality borders. And these comprise no less than 18 different catchment areas that bring their water to the Indian Ocean through 17 estuaries. Next slide. And you can imagine that all that complexity brings about quite some challenges and also calamities, unfortunately, at quite a regular basis to the municipality of Durban. The most important one being flash floods due to very heavy rainfall. Durban has got a very humid subtropical climate. These flash floods can endanger settlements, as you can see in this aerial photograph. Next, please. Or infrastructure, as you see here. Next, please. It can even trigger landslides, as you can see from this aerial shot. Next, please. And all the stormwater runoff brings along a lot of debris and pollution that ends up either in the estuaries or at the coast or even in the harbor basins of the large harbor of Durban. Next, please. And coastal flooding is another hazard. Can you go back to the previous one? One back. Thank you. This was an event in 2017 when very large swell waves hammered the Durban beachfront, which normally is a very nice and pleasant place, but this time not so much. Quite big flooding, and it was a big hazard to all the people walking along the promenade, as you can also see here. Next, please. And finally, all these estuaries of the municipality have a lot of complexity going on in the estuary mouth. A lot of sediment dynamics, estuaries sometimes even closing off periodically, which then can cause all kinds of water quality related issues, but also flooding. Next slide. Around 13 years ago, Obscape was selected by the municipality of Durban to set up an extensive real-time monitoring program to address all these complex water systems. And by the time Obscape was still a local survey company in South Africa, the task posed by the municipality was very extensive. Around 200 different sites had to be monitored real time, different types of hydrological parameters, which involved a wide range of different sensors. However, that all had to be done with a fairly limited budget, and there was a small team available for field operations, so to install and maintain all the equipment. At Obscape, we very soon realized that this was not going to happen with conventional off-the-shelf equipment, either for financial or operational reasons. So the only solution we were left with was to start developing our own equipment. And that's actually what started our transition from a survey company into a manufacturer of survey equipment, of monitoring equipment. In the early days, the equipment that we developed for this project didn't look very pretty, as you can see in these images, but it got us going, and we made through a significant development over the years, which is what I'll show next. You can go to the next slide. With the development of our product range, we always took into account the following design criteria. First and foremost, everything had to be affordable, since we were working with a limited budget. But then equipment also had to be robust, and it's easy to make something that's cheap, but it's not easy to make something that's cheap and long-lived. So the robustness was really also a big design challenge for us. And finally, it also had to be low maintenance, since we were dealing with that limited capacity to do installations and maintenance in the field. So all the equipment had to be able to run by itself for a long time. So this is the product range that we developed: a water level gauge, a time-lapse camera, a weather station, a rain gauge, and a wave measurement buoy. And you can see a large degree of similarity among especially the top four instruments on the top row. They are all based on what we call the power and telemetry module, which is that white and black rectangular milk carton shaped thing. It has solar panels on the sides. Those are the black faces that you can see, those black panels. We can either connect external sensors to these to this power and telemetry module, as we did for the weather station and the rain gauge, or we can integrate sensors into the housing directly, like we did for the level gauge and the time-lapse camera. Next slide, please. All these products from the product range have the following features. They all have real-time connectivity through the 4G network, or if that's not available, the satellite network. They are all solar powered, and those two properties make them completely wireless. So there is no need for power or data cables. You just hang them in a tree, strap them to a cable, to a pole, or bolt them to a wall, and off you go. The settings of the devices and firmware updates can be controlled over the air, over the 4G connection. They have a generic third-party sensor interface, which allows us to basically connect each and every off-the-shelf sensor to this power and telemetry module. So you can basically turn it into a real-time monitoring device for anything. We also supply camouflage sticker kits, because you can imagine that Durban is a theft-sensitive environment. In the bottom right picture, you can see that we have applied sort of a vegetation theme sticker kit to a device to hide it a little bit and make it blend into the environment. We do that for urban, more concrete type environments as well. Then also the data of all these real-time devices are being sent to the Obscape data portal, which is a very extensive environment for data viewing, data analysis, data management, and also for downloading your data. And a lifelong license for this data portal is included for free with the purchase of all these devices. Next slide, please. And these are some pictures to show you the deployment of these instruments for the eThekwini municipality. This is a level gauge hanging down from a bridge. The level gauge has got a radar sensor at the bottom of the device, and it measures the distance to the water surface, and that's how it measures the water level. Next, please. This is a time-lapse camera that sends images to the data portal at a user-defined interval. Next, please. And this is a rain gauge installed in the field. Next slide. This is the full overview, and it's also the current status of the monitoring network. So you can see all these sensors of different types deployed throughout the Durban municipality, which at the moment totals to 109 monitoring stations, and we are still expanding that towards 200 before the end of the year. So there's still work to be done there. You can go to the next slide. The reason why the Durban municipality is collecting all these real-time observations is twofold. On the one hand, they use it for validating their numerical forecasting models, but on the other hand, the sensors are also their boots on the ground. It provides the actual ground truth. So the forecasts are nice to plan ahead in case you see a potential disaster approaching. But if you have to do the disaster management, being able to see and to read what's actually happening in the field is very, very valuable. Next slide, please. And then I'll finish off with the case of the April 2019 flooding, which was triggered by very heavy rainfall. I'll first set the scene a little bit with a few aerial pictures of flooded infrastructure over here. Next slide, please. A flooded settlement, and this image was shown from a different angle before already. Next, please. And this was what the marina as part of the Durban harbour looked like during the floods. Next slide. So luckily we had our sensors in place by the time, and this screenshot is taken directly from the Obscape data portal. It shows the cumulative rainfall over the event from all the rain gauges that we have installed. So you can see that up to 340 millimeters of rainfall fell on that particular day, the 23rd of April 2019. Next slide. Let's now zoom in on the mouth of Amanzimtoti River, which is south of the city of Durban. This aerial photograph shows the flooding in that area, and we also had some sensors in place there. Next slide. The top graph, and these are data from our sensor network. The top graph shows the rainfall intensity, hourly rainfall from a nearby rain gauge. And the bottom graph shows the water level in Amanzimtoti River. And you can very clearly see the response of the water levels that rose sharply as the rainfall became more intense. Next slide, please. And we also had a time-lapse camera in place. This is what it looks like under normal circumstances a few months prior to the event. Next slide. And this is what it looked like during the flooding. So at this particular location, there wasn't too severe flooding outside the river banks, but still quite a big increase in water level. And you can tell from this image that the flow velocities increased quite a lot. Next slide. Then this is Umbilo Canal in the back of the Durban Harbour. Again, this is what it looks like under normal circumstances. Next slide. And then this was during the storm, and this imagery is also taken from one of our time-lapse cameras, and you can see the huge amount of debris that washed out of this canal, and that, as you saw on another picture at the start of the presentation, ended up in the harbour as there's a lot of debris and a lot of plastic and other trash floating around. Next slide. These are the water levels recorded by one of our level gauges in the Umbilo Canal. And you can see that the event on the 23rd of April was a very sharp trend break from the normal spring neap tidal cycle, especially the low tide water levels rose significantly for a few days. Next slide. And then finally, this is a time-lapse camera situated at the beach. And this is a picture from the 23rd of April, so the day of the event. And now everything at the beach still looks quite okay. Next slide. But then a few days after, this is on the 25th of April, 2 days after, you can see this line of wreckline material, a lot of plastic and other debris that did not only end up in the harbor basin, but also ended up on the beach. So a lot of cleaning works were required afterwards. Next slide. So by showing you all of this, I want to make the point that by doing this project for the Durban municipality over the past 13 years, and through the development that we have undergone at Obscape, we have made state-of-the-art environmental monitoring accessible to anyone. I would like to thank the Durban municipality for their input for this presentation and for all their support, and I would like to thank the audience for their attention.
Thanks, Max. We have one or two questions for you. One of the question is, can you briefly explain the functioning of the wave buoy, please?
Yes, the wave buoy is based on motion sensors, mainly an acceleration sensor, so the buoy moves up and down with the waves, and by recording the motion of the buoy, we can derive all the relevant wave parameters as well as the directional wave spectrum.
One other question is that you mentioned the data portal. Is it free to use?
Yes, it is included with the device, and it's an unrestricted license, so you can use it as long as your device lives.
And are these units completely wireless? Some of the units that you showed?
Absolutely, they are completely wireless. So the solar panels provide the power, and the 4G modem and the satellite modem provide the connectivity.
Thanks, Max. We have one or two questions still in the Q&A box that maybe you would want to, answer to some of the attendees.
I will address those.
Thanks, Max. This brings us to the last presentation that we have scheduled for you today. We have tried to cover different areas of use of innovative technologies in different sectors. And I would now like to invite Mr. Rahul Moral from Akista, who's going to talk about these innovative pumps that do not use any electricity or do not use any fuel. Over to you, Rahul.
Yeah, thank you. Good evening to all present, to the panelists and the guests. I'd like to thank the panelists for their interesting presentation so far. Moving on to the presentation from Akista. So the topic is, as it says, is sustainable solutions for irrigation in India. Akista's Bursa pump. We are looking at mostly at India, but I also have some case studies from other countries where we are present. Next slide, please. Yeah, so the introduction, as I said, sustainable solutions for irrigation in India. What is our solution? What is Akista's solution? They are hydropowered pumps. We call them the Bursa pump. As you can see, there are two pumps. This is from a picture in Nepal. Moving on to the next slide. Next slide, please. Who's Akista? I'd like to take the time here to introduce our company. We are a company developing and deploying hydropowered pumps for irrigation. Our mission is to provide sustainable hydropower pumping solutions that have a positive economic, environmental, and social impact. We were founded in 2013 in the Netherlands, and we have a team of 30 people, with 10 of us in Netherlands and the rest of us divided between our entities in Nepal, Colombia, Indonesia, Malawi, and India. India being the newest entity. And we have products in over 20 countries. Next slide, please. Akista in India, we were founded in 2018, late in 2018. Currently, we are a team of 5 in Mumbai and in Guwahati, Assam. I myself am speaking to you from Guwahati, Assam. Our warehouse in Mumbai, we have a warehouse in Mumbai which handles the storage and the assembly and distribution to the rest of the places, including abroad. Right now, we account for 60% of global production in India. And we have plans to have the entire production and assembly process moved to India in the coming future, in the next 1 or 2 years. Like I said, we have an office in Guwahati, and the first pumps in India have been running in Assam since 2019 in partnership with Selco Foundation and SESTA. One is a NGO and the other is a development funding agency. Next slide, please. Next slide, please. Thank you. Thank you. One back. Yeah. So this is a picture of the hydro pump. We call it the Bursa pump. We own the design. We've got it. We have the patent on it also. It was pending for a while, but now we've got it. The picture you see is a simulated picture, of course. This is from a picture in Nepal where a pump has been installed eventually. So the Bursa pump it's an award-winning concept. We've had the Siemens Innovation Award and the Philips Innovation Award and some other awards. The USP of the product, if you can move on to the slide, please. Yeah, so the USP of the product is it needs no fuel for operations, needs no electricity, therefore has no emissions, and because of the design itself, virtually no maintenance. And unlike other renewable energy decentralized appliances, this has, because it's hydropowered, operations are 24/7. Next slide, please. This is the Barsha pump again, picture from Nepal, which is, I really stress here on Nepal because we've had tremendous success in Nepal and we've been operational there for a while now. These are the pumps, as you can see, placed in a rural area. Then next slide, please. Okay, so more on the Barsha pump. It's basically a water wheel propelled pump that utilizes the kinetic energy, the flow of the rivers from rivers and canals, and converts that into mechanical energy, and then that builds pressure, and then with that we transport the water to where it's needed. So being a hydropowered appliance, it doesn't need fuel or electricity to be operated, so we stress on that. Has no operational costs that way. It can be used in, the design itself is quite versatile, so it can be used in rivers, canals, different kinds of rivers, shallow, deep, and also streams. Streams that run throughout the year and streams that dry up. The design itself is quite versatile, like I said, so it can be implemented in a lot of, the scope of implementation is quite wide. Next slide, please. The output performance and technical description of the product is in lab tested conditions. We have found out that it can pump up to 20 meters high, depending on the flow rate, for a flow rate of around 1 meters per second. But in the field, we have discovered, we've observed that depending on the flow of river or the stream, rivers that are very fast moving or rivers in the monsoon season, rivers which are very full, the output performance is much higher than observed in the lab. So it can pump up to a distance of 2 kilometers or up to 20 meters high. Depending on the flow rate of the river, the output is anywhere between 20,000 to 80,000 liters per day. Can has multiple uses. Can be used for irrigation, aquaculture, livestock farming, integrated farming, and can be used with smart water management techniques like drip irrigation systems, sprinkler systems, furrow irrigation. It's also compatible with modern storage tanks and storage ponds. And like I said, it can be used in rivers, streams, and canals. Next slide, please. So this is one of the things that we have stressed, that our team has stressed while designing the product, is to make it easy and flexible, easy for local populations, because we plan to implement this in mostly agricultural areas in our country and in neighboring countries. That means rural areas. So this is the design itself is again quite easy and flexible for local implementation. It can be assembled on site. No specialized tools needed. We don't need infrastructure. Easy local maintenance. People who have seen the installation process can then help others to install it themselves, and also help with maintenance, which is very little anyway. It's compatible in versatile installation scenarios, and possible, and the operationality in rivers and streams is also quite low. It can function in very slow moving rivers and streams. As you can see here are pictures of the four different versions. The first one, the top right one is in a river, floating version. The one next to it is a standing version in a shallow river. And the two below, the one on the right is mounted in a canal, and the other one is again on the right is a floating version. The next slide, please. So as I've said, it's a versatile design. Its applications are many, and here are just a few of the applications of the Barsha pump. We've used it in irrigation, flood irrigation, which is typically used in our country. It's also compatible and very effective with smart water management systems like drip irrigation, sprinkler systems, and like I said, it's compatible with modern storage tanks that are portable, mobile storage tanks, and storage ponds. Can be used for furrow irrigation, livestock farming. We have a few very good cases, very successful cases from Africa, where it has been from Malawi, where it has been used in livestock farming. Also aquaculture, because the pump itself pumps irrigated water, so it's very good for aquaculture, and we have plans to implement it in aquaculture in Assam and in the other northeastern states. Next slide, please. The benefits of our pumps. So like I've been saying, zero operational costs. That is the first and the most important benefit of our pumps, because our target audience is, or our target user, or the end user is basically, they are going to be farmers. In our country, farmers don't have very good means to procure expensive items, so and have operational costs. So zero operating costs, that's very important. Virtually no maintenance, because it has been designed in such a way, it's robust, and the materials used in the pump are high quality. So virtually there is no maintenance, and little maintenance, little damage that happens to the pump due to debris in the river or something similar, we do that free of cost. Right now, because we are the demonstration phase, we want to find out what are the real world scenarios that the pump will face. But in the future, we will develop a system for a more comprehensive system for maintenance. No emission of greenhouse gases. That's very important, because we don't use any fuel, no electricity. So obviously there are no emission of greenhouse gases. And also the places where we are implementing it right now in India are basically clean, pristine environments. So it's always good not to pollute them. Constant operation, I said this before, it's competition in renewable, in similar products in the renewable energy area, like for example, solar pumps or other electric pumps. They don't, solar pumps will not operate, they have operationality problems, will not operate 24/7 throughout the year. But Barsha pump, a river or a stream that runs perennially, means it will operate 24/7, 365 days a year. As we have seen from our case studies, once one of our pumps replaces the conventional pumps, the farmer can make up to 70% cost savings. Water savings, because we suggest, we advise the farmers to use smart farming irrigation techniques like sprinkler systems and drip systems, so that adds to water savings as well. Like I mentioned, allows for irrigation, good for aquaculture and pisciculture. Because in India, mostly farmers are dependent on the monsoons for their harvest, farmers who will benefit from this intervention can have a harvest 2-3 times a year, so they don't have to sit and not do anything during the dry season. Next slide, please. Here's some cost comparisons with other conventional pumps. Total cumulative costs over the lifetime. The Barsha pump is by far lower than any of the other competition. Of course, conventional pumps are widely used, but they are harmful for the environment and expensive to operate. And also with electric pumps and solar pumps, cumulative costs over its lifetime, the Barsha pump is much lesser. Next slide, please. We have some more cost comparisons. Total annual costs, again, if you see, the Barsha pump has no operating costs, so the total annual costs also come to be very low, much cheaper to purchase than solar pumps. So then again, when it comes to costs, Barsha is the clear winner. Below in the graph below is the cost per volume. That means the amount of land that the Barsha can irrigate, and that then again it comes out a clear winner with its competition. Next slide, please. Thank you. Barsha pump in India. So we are at our situation in India is right now we are at a place where we are involved mostly in production and of course demonstration through implementation and pilot projects. If you see here, there are a few pictures of our warehouse where we store the parts before assembling it, and then we have some pictures of some installations in remote locations. So the next slide, please. Our vision in India is to enable affordable and sustainable access to irrigation and bring back the love for surface water in harmony with nature. Exactly. So one of the main problems that we wish to address is stop the overexploitation of groundwater and bring back the usage of surface water. There are a lot of areas in the country where there are farms next to water sources, but the farmers have a problem of getting water from that water source to their farms. So this product aims to address that. Next slide, please. All right. Yeah, thank you. So this is one of our focus areas where I am situated right now, Assam, and we have found out that given the terrain and the hydro potential in the state, we have a potential for around 700,000 acres where we can implement the Barsa pump. That's one a better case scenario. It will not be out of that's almost 30% of the land. That will not be the same for other states, but I just wanted to show this as a case study. As you see, the Brahmaputra runs through Assam, and there are many tributaries and distributaries along the way. Although, if you look closely into the map, you can see that the brown areas are regions which are not suitable for the pump. If you look even closer, you'll see there are green veins running all across it. That means those are suitable for the implementation of the pump. Which again means that the Barsa pump can be used almost in half the area of Assam. Moving to the next slide, please. Call to action. This is very important for us because we've noticed from our other case studies, from our experience in Nepal, that the real effectiveness and the real change from the Barsa pump can be noticed only when it is scaled up and it is implemented in large numbers. So that's why it's very important for us to work on policy awareness, because in our country, farmers can't purchase an item which costs 1 lakh or close to 1 lakh on their own. They need some kind of institutional help, financial help. So policy support in the sense that we need to get subsidies, include the appliance in the list of subsidies. That is what has happened in Nepal, and further down the line, we need distribution partners, distribution partnerships. One slide back, please. Distribution partnerships to help us with the logistics to have a reach throughout the country, and then of course demonstration pilots with NGOs and development agencies. Next slide, please. So these are some of the cases from around the world. I'd like to stress on Nepal first because we've been there the longest and we've seen some really encouraging results from Nepal. This is what we call a series installation where 2 Barsa pumps have been installed simultaneously on the same river. So this can the combination of these 2 pumps can irrigate an area of up to 5 hectares of land. So in a country like Nepal, 5 hectares of land will employ a lot of people. There'll be shared ownership, so a sizable quantity of people will be affected by this kind of an implementation. Of course, this is being used for vegetables and fish farms. So they have different kinds of. So they have a pond. They grow vegetables in and around that area. So yeah. So the next slide, please. Again, this is another picture from Nepal where we have slightly modified the conditions of the pump to make it more efficient. As you see, we've built a dam, and this is what we call a breastshot, where the water then falls from a height. So on top of kinetic energy, it has some potential energy as well. So the pump runs more efficiently for really slow-moving rivers or streams, which can be manipulated manually by people around. This is an option to increase efficiency. And then this is used in a farm that grows tomatoes and other water-intense crops. Next slide, please. So here are some figures from the impact achieved in Nepal. I have these figures. These figures are around 3 years. These figures are from 2017. So if you can see, that's we were there for 3 years before that. So this is collective data for 3 years. So in 3 years, we've achieved 200 hectares of land have been irrigated, around 300 million liters of water has been pumped, and 5,000 people have benefited directly or indirectly. And the most important that we feel in this time, especially in our region, is we have saved 100 tons of CO2 emissions from agricultural use, generated from agricultural use. So, like I said, this is data from 3 years ago. So the current data is slated to come out this year, but of course, obviously it has been delayed because of the COVID situation. But the new set of data that we will receive will be considerably higher from Nepal. Moving on to the next slide. some case studies from some other countries. This is drip irrigation, Bursa pump being used to drip irrigate a vegetable field in Turkey. So this, as you can see, this is a floating version. It's a slightly deep river, a few meters deep. So a standing version will not work. And like I said earlier, the design is versatile, that we just attach the floats and it's good to go. Moving on to the next slide. Just a second. If you can see, they're using a storage tank. So they bring the water from a certain distance and they store it in the tanks, and then from there, the field is being irrigated. So the pump does not need to be, the farm doesn't need to be next to a river or a stream per se. It can be a certain distance away, just that it needs to be within that 2 kilometer or 3 kilometer distance from where the pump can successfully pump water. Next slide, please. This is again from another case from Spain. This is a floating version of a pump installed in a small canal, and it's being used for olive oil, for producing olives and tomatoes and cherry tomatoes and some other vegetables. So they've had great success. They used to spend a lot of money. Farmers in Spain, in Europe, spend a lot of money on irrigation. So operational costs, by that I mean operational costs. So they are positive about switching to an appliance that has no operational cost. It's just the one-time setup cost. That's a system that a lot of farmers in Europe can afford. Unfortunately, here it's not the same. So the farmers here need some kind of institutional or financial help. Moving on to the next slide. I'm just a couple of more slides. I'm almost done. So this is this is the last slide. So this is from a shallow river in Panama. Again, like I said earlier, it's being used for livestock farming, very dry area. So the livestock needs to travel quite a distance to get to their grazing grounds. And that is not very helpful for the farmers. So they've used here the Bursa pump. It's in a very shallow river. So the floating version, I'm sure the picture here, there's a little bit of modification that has been done. You can see the stones on the floats to keep it there, but an easier fix would be just to unscrew the floats and keep it as the standing version. So like I said, again, demonstrates the versatility of the pump, and places where it can be implemented, where it has the right conditions, it works really well. So yeah, so those are the next slide, please. So that brings me to the end of the presentation. So our, like I said earlier, we believe that we should, in the current age, saving water. It's basically very important to save the important things. So that's water, energy, and costs. And by doing that, if you can also generate income and make an improvement to people's lives, I think we achieve a lot. So with that, I'd like to end. Thank you for your patience. I know this was the last presentation, but I tried to keep it as short as possible.
Thanks. We have a few questions to you. I know we are a little beyond our scheduled time, but since we have a lot of people here and also a lot of questions, I thought I'll just extend it a little bit. I will not go on to the questions with regards to pricing and all, but we have certain few questions. So one question, Rahul, is that is there any criteria to operate these pumps on a minimum water level of the river?
Yeah, so the criteria are the river needs to have a level of at least 18 inches, 12 to 18 inches. We recommend 18 inches minimum, but we've seen that it also works in rivers where the water level recedes below 12 inches. Just that the water needs to be in contact with the paddles, if you've seen the picture. So shallow rivers, shallow streams, not a problem. Anything above 12 inches works.
Another question, Rahul, is that what happens during floods? Will this pump?
Yeah. So during floods, if we have a unit which is a standing version and it's in a shallow river, and during floods the water level rises tremendously, the best thing to do is remove it for the time, because within a month or two the floods will recede. Other versions, floating versions in rivers which are prone to flooding, we have a system to secure it using ropes to the bank. So we don't, if the river is too big, we don't place the pump in the middle of the river. We place it on the sides. So it's very easy to secure. And also again, with the floating version, with the standing version also, we have something called floor floor hammers. So we hammer them floor. So floor anchors. So we hammer them into the bed of the river, and that saves it from being pushed away in the river by the current. And also the pump weighs around 100 kilos. So the flooding needs to be of considerable amount for it to be displaced.
Okay, one more question is, can these pumps be used for dewatering of low-lying areas?
Yes, yes. But then again, one has to understand that the source of the water has to be under that the 2-kilometer distance. It can't be too far away. So the water source that we wish to take the water from needs to be within that distance.
Max, are you there? Max, are you still there? We have a question for you, Max. Maybe I think Max is not in his seat. So, we have a lot of questions that are still there in the box, but since we are way beyond time, what we will do is that we will share these questions with all of our presenters with your email IDs, and we will request them to, answer these questions for you. Any questions that were related to the price and the dimensions, I'm sure you could get it onto the websites of these respective companies. This brings us to the end of day 3. We have had a wonderful session, today. And, I would like to thank all the presenters who have taken time out of their busy schedules to share their inputs with us. I'm sure the audience would have benefited greatly, from the knowledge that you have shared with us. Day 4 tomorrow for us is on recycle and reuse. We have some wonderful case studies from Mumbai, from Singapore, from Paris. And I would like all to, please take use of this opportunity to go through these presentations tomorrow. So please do join us at 4:30 p.m. tomorrow for day 4 of the event. And we would just request you to, if you could quickly share, your few times to fill in the poll that we have scheduled for you. And thank you all for your patient hearing, and we'll see you all tomorrow. Thank you.